Welcome to my YouTube channel, A Binary of Civil.
Today I am going to solve the sixth assignment of design of reinforced concrete structures. It is related to slab portion. The first question is, he has given in the list 1 is a type of a slab, and in the list 2 it is span to overall depth ratios. Span to overall depth. Okay. So now he has given the data two-way slab, solid slab for shorter spans up to 3.5 meters. So shorter span maximum limit is 3.5 meters, adhering to vertical deflection limits for loading class up to 3 kN per meter square, reinforced with HYSD bars. So for all these conditions, if it is simply supported slab, span to overall depth ratio is 35. If it is continuous slab, this ratio will become 40. So this will be applicable only for FE 250. Okay. Now he has given in the problem the reinforcing bars are high yield deformed bars. So if we are intended to use high yield deformed bars, this span to effective depth overall depth ratio has to be multiplied with 0.8. Then this will become 28. 40 into 0.8 will become 32. So for simply supported is 28. So it is A2, and continuous B it is 32. So it is B3. So A2, B3. So for question number 1, answer D. Clear? These ratios are very important. Coming to next question. Following are the details of an unrestrained reinforced concrete slab simply supported on all 4 walls. There is no restrainment, and the given slab is a simply supported slab, and he has given data 4.5 divided by 6 meter and 200 mm overall thickness of the slab, and it is live load is 10 kN, dead load is, and floor finish is 1 kN per meter square, M25 FE415, and clear cover is 20 mm, and bottom reinforcement is 12 and top reinforcement is 10. So generally bottom reinforcement and top reinforcement he has given different diameter bars. So generally for a simply supported beam, the top is compression and the bottom is tension. So bottom it is tension and the top is compression. So you need to observe this, and he has given 5 statements. We need to check whether those statements are right or wrong. So let's go with the solution. So in the second solution he has given live load, that is L is equal to 10 kN per meter square, and dead load is equal to, he has given thickness of the slab as 200 mm, that is 0.2 into 25. So you will get it is 5 kN per meter square, and floor finishing he has given it is 1 kN per meter square. So total will become 10 plus 5 plus 1, it is 16 is total load on the slab, and we need to calculate factored load. For design purpose, we need to calculate factored load by multiplying the given load into 1.5. So it is 1.5 into 16, we will get it is 24 kN per meter square. Clear? So now observe the statements. The slab carries a dead load of 5 kN. So this statement is correct. Statement 1 is correct. The design load as per the limit state method is 24. So the factored load as per calculation of limit state method, we got the value of 24 kN per meter square. So the statement 2 is also correct. So now coming to, he has given the dimensions of the slab as 6 meters, 4.5 meters. That is, we need to calculate Ly by Lx. 6 divided by 4.5. The value is 1.33. So this is less than 2. When longer span to shorter span ratio is less than 2, this will be two-way slab. Clear? So statement 3 is also correct. So the given slab is a two-way slab, and statement 4 and 5 are related to effective depth along longer direction as well as in the shorter direction. Now effective depth along x direction dx is equal to, thickness of the slab is 200 mm and clear cover is 20 mm, and along x direction the diameter of reinforcing bar is 12 mm. So that is 12 by 2. So you will get it is 174 mm. And effective depth along y direction is 200 minus 20 minus 10 by 2. So it will be 163 mm. So the given statements are 174 along x direction, along shorter direction. So here you need to mention the shorter direction as x direction and longer direction as y direction. So the statement 4 is correct. But the statement 5, the effective depth along y direction is, we got the value as 163, but he has given it is 125. So the statement 5 is wrong. Remaining all the 4 statements 1, 2, 3, 4 are correct. So he has asked, which of the following statements are incorrect? Incorrect statement is only 5. So answer B for question number 2. Clear? Next question. Now, following are the details of an unrestrained reinforced concrete slab simply supported on all 4 walls. The data is same as in the earlier problem. So 4.5 by 6 meter, 200 mm slab thickness, 10 kilonewton and 1.1 kilonewton per M25 Fe415 20 and 12 10 mm bars. So same data. Okay, there is no change in the data. So now in addition to the earlier problem, we need to calculate. So what is the total load? So total design load we got in the earlier problem as 24 kilonewton per meter square. And Ly by Lx ratio, that is 6 by 4.5 is equal to 1.33. So based on the value of Ly by Lx ratio, we need to calculate moment coefficients along x direction, that is along shorter direction, as well as in the y direction, that is along longer direction. So now from the table Ly by Lx and alpha x coefficient, Ly by Lx is 1.3, the alpha x value is 0.093. This value you can get it from IS456 in the table. And for 1.4 we got it is 0.099. We need to calculate 1.33. So alpha x value corresponding to 1.33 value of Ly by Lx. Clear? So that value I got it is 0.0948. So finally alpha x value, that is moment coefficient along shutter span, that is along x direction, we got as 0.0948. Clear? So he has given the statement as this only. So the first statement is correct. Okay. And now second statement is the moment coefficient along longer direction, that is along y direction, we need to calculate based on Ly by Lx ratio itself. So here you can see Ly by Lx and alpha y. Ly by Lx 1.3 and 1.4. Corresponding to 1.3, alpha y is 0.055. Corresponding to 1.4, alpha y is 0.051. Now we need the value of alpha y corresponding to 1.33 value of Ly by Lx, that is 1.33 here, and we got it is 0.0538. So here you need to observe is this entire data you will get it from Indian Standard 456 code. Okay. So alpha y value is equal to 0.0538. So statement 2 is 0.0825. We got it is 0.0538. Statement 2 is wrong. Now coming to moment along x direction is equal to, we have a formula alpha x w Lx square. Alpha x value is 0.0948. W is the total design load. So we got it is 24. And Lx, that is shorter span, 4.5 whole square. This will be 46.0728 kilonewton meter. And moment along longer direction, that is My, is equal to alpha y w Lx square. Very confusing formula, this one. During calculation of moment along y direction, that is along longer direction, we need to use shorter span square, not longer span square. Clear? So you will get this value 0.0538 and into 24 into 4.5 square, that is equal to 26.15 kilonewton meter. So statement 3 is this one, statement 4 is this one. You can check here. 46.08. So this is correct statement. He has given moment along x direction is correct. And moment along y direction he has given 46.48. But we got it is 26.15. So statement 4 is wrong. So he asked which of the above statements are incorrect. So from the observation we can say that statement 2 and statement 4 are incorrect. So answer is answer is C for question number 3. Okay. Very important questions all these. The most important concept here is when you are calculating moment along longer direction, you need to use shorter span, not longer span. Clear? So now, coming to question number 4. A simply supported reinforced concrete slab of effective dimensions 4.5 meter by 6 meters is carrying a uniformly distributed load, that is UDL. He has given as UDL is equal to 16 kilonewton per meter square. So then calculate factored UDL. According to limit state method of design, we need to calculate factored UDL. 16 into 1.5, that is 24 kilonewton per meter square. And he has given thickness of the slab and cover and reinforcing bar. So effective depth D is equal to overall depth is 200 and clear cover is 20 mm and half of reinforcing bar dia is 12 by 2. So we will get it is 174 mm. And now we already know the value of Ly by Lx, that is equal to 6 divided by 4.5, that is equal to 1.33, and same alpha x as 0.0948. And now moment along x direction we already calculated in the last problem, that value is 46.08 kilonewton meter. Now what is the required area of steel in shorter span? Here we know the value of moment along shorter span and we know the value of reinforcing bar as 12 mm. Now we need to calculate how much amount of reinforcement has to be provided in shorter span. So we have a formula in the IS 456 code. Mx is equal to 0.87 Fy AST into D 1 minus AST Fy divided by FCK BD. Very important formula. So Mx we got as 46.08 into 10 power 6. I am converting this kilonewton meter into Newton mm. That is equal to 0.87. Fi is 415. AST we do not know. And D is equal to the effective depth 174, we just calculated. And now 1 minus AST into 415 divided by FCK is 25. B it is 175 and D it is 1000. Clear? So from this expression the only unknown is AST value. So AST is equal to 793.65 mm square. So the answer A for question number 4. Okay. Coming to next question. A simply supported reinforced concrete slab of effective dimensions 4.5 meter and 6 meter is carrying a uniformly distributed load 16 and M25 Fe415 thickness of the slab. Now the data is same as earlier problem. In the earlier problem he asked us to calculate the amount of reinforcement that is required to be provided in the shutter span. Now in the same shutter span, what is the spacing of the reinforcing bars? The spacing of reinforcing bars of 12 mm diameter. So we need to calculate spacing. Spacing is equal to small AST divided by capital AST into 1000. Small AST is area of one reinforcing bar of dia 12 mm, that is pi by 4 12 square divided by total how much reinforcement we need to provide 793.65, because in the earlier problem the total reinforcement required is 793 into 1000. So we get it is 142.50 mm. Clear? So answer D for question number 5. Next question, very important conceptual question. To prevent cracking of edges, the corners should be provided with. Generally, we will provide reinforcement for positive bending moment as well as negative bending moment. In all the situations, when slabs are one-way slabs, that is, one direction length will be very high. In that cases, the corners will get easily affected to cracking. To avoid this cracking, we need to provide torsional reinforcement. That is, the corners are subjected to twisting moments. To resist this twisting moment, we need to provide reinforcement at the corners. That particular type of reinforcement is called torsional reinforcement. Okay. So this we can provide it like as you can observe here in the diagram in these corners. In addition to the positive as well as negative reinforcement in the corners, we need to provide this corner reinforcement. Clear? This additional reinforcement is called torsion reinforcement. So the answer is C for question number 6. And it's very complete theory question. Question number 7. Following statements regarding torsional reinforcement. So coming to first statement, it shall consist of, what is this here? It is torsional reinforcement consists of top and bottom reinforcement. That is, each layer of bars placed parallel to sides of the slab. So all the layers, the reinforcement shall be placed. It is parallel to sides of the slab and extending from edges to a minimum distance of 1/4. So that is from the edge, the minimum extension required is 1/4. That is, he has given the extension as 1/4 in the given statement. But what IS 456 say, it is extension is not 1/4, it is 1/5. 1/5 of the shorter span. Okay, so for that reason, the statement 1 is wrong. Clear? And now coming to second statement, the area of reinforcement in each of these 4 layers, that is tension reinforcement and compression reinforcement, along with these 2 reinforcements, torsional reinforcement can be provided extra 2 layers. So total layers will become 4 layers. Shall be 3/4, that is 3/4 of the area of required for maximum mid-span moment. Clear? So the statement 2 is correct. Coming to statement 3, for a corner contained by edges over only one of which slab is continuous, area of reinforcement in each these 4 layers shall be 3/8. Very important. If the ends are not continuous, the reinforcement amount is 3/4. If the ends are continuous, the reinforcement amount is 3/8. That is half of 3/4. You can observe this point. Statement 3 is also correct. Now final statement is, torsion reinforcement need not be provided at any corner contained by edges over both which the slab is continuous. Clear? When both edges of the slab, that is along x direction, along y direction, when the slab is continuous, in that case, no need to provide any torsion reinforcement. In that particular case, the slab at that location need not be subjected to twisting moment. For that reason, it is not required to provide torsion reinforcement. So statement 4 is also correct. He asked which is incorrect statements. Only one. Answer A for question number 7. Clear? Now coming to question number 8. If area of steel reinforcement corresponding to maximum midspan moment is 500 mm², calculate area required for corner reinforcement of the slab simply supported on both edges and meeting at the corner. So very important, you need to remember. So that is 3/4 of total area. area of reinforcement corresponding. So that is 3 by 4 into 500. It will become 375 mm square. Clear? Answer C for question number 8. Coming to question number 9. For a factored load 15 kN per meter square inclusive self weight on an interior panel of 4.2 meter by 6.25 meter effective dimensions. So it will be, he has given so much data, he has given some problems, negative moment, positive moment, and negative moment on the edges and positive moment on the shorter span. So that is 4 statements, 2 statements corresponding to negative and positive moments of longer span and negative and positive moments of shorter span. So now coming to the solution, he has given factored load 15 kilonewton per meter square and Ly by Lx is equal to 6.25 divided by 4.8 is 1.488. Now we will calculate the negative as well as positive bending moments corresponding to longer span. That is longer span negative moment at the continuous edge. So that is along longer span, whether we need to use alpha x or alpha y. Longer span, that is y direction, we need to use alpha y. So corresponding to 1.488 value of Ly by Lx, alpha y is 0.032. This value we can get it from code book. And my is alpha y w Lx square. Alpha y is 0.032, w is 15 and Lx square is 4.2 square. It will be 8.47 kilonewton meter. And statement 1 is incorrect. So negative moment corresponding to continuous edge for longer span is 18.75. So but we got it is only 8.47. Statement 1 is incorrect. Coming to statement 2, he has given it is positive moment at mid span. So in this case alpha y will become 0.024. So my is equal to 0.024 into 15 into 4.2 square. It will be 6.35 kilonewton meter. Statement 2 is correct. So it is statement 2 is incorrect. Okay, so we got it is 6.35, but here he has given it is 14.06. Statement 2 is also incorrect. Now coming to, these are all the negative as well as positive bending moment in the longer direction. Now we will calculate along shorter direction. So in this case, negative bending moment, first one, alpha x will become 0.0528, mx is equal to alpha x w Lx square. It will be 13.97 kilonewton meter. So 13.97. So option 3 is correct. And positive bending moment, alpha x will become 0.0408 and mx will become, it will become 10.78 kilonewton meter. So 10.78. So statements 3 and 4 both are correct, and incorrect statements are 1 and 2. Okay, so the answer C for question number 9. Clear? Now coming to last question, he has given the data, an interior panel of 4 by 2 into 6.25 meter effective dimension subjected to a factored load 15 kN per meter square including self weight. The slab is provided with main reinforcement 8 mm, thickness is 150 mm, clear cover 20 and M20 Fe415 steel. So now coming to, first of all we will calculate the effective depth. Small d is equal to 150 minus 20 minus 8 by 2. So that is 126 mm. This is the effective depth. Factored shear WU Lx by 2. This is factored shear. WU is 15, Lx is 4.2 divided by 2. it will become 31.5 kilonewton. So he has given it is 15, but we got it is 31.5. Statement 2 is incorrect. D required is equal to mu divided by 0.138 FCK BD. So if you will substitute the values, the maximum bending moment out of above all 4 is 13.97. So you will get it is 72 mm. But we have provided the effective depth as 126. The required depth is less, but we provided more. Obviously, it will become under reinforced section. But he has given in the statement 1, it is over reinforced. So statement 1 is also wrong. And now coming to, by following equation, mu is equal to 0.87 Fy AST D into 1 minus AST Fy divided by FCK BD. So by using this equation, you will get AST as 324.41 mm square. So how much he has given this? 324.41. Answer C, that is option 3 is correct. Now spacing we can calculate. Spacing S is equal to small AST by capital AST into 1000. So the reinforcing bar that he is provided is 8 mm. So small AST will become 8 mm, that is pi by 4 8 square, and the total reinforcement we need to provide is 324.41 into 1000. So you will get spacing as 155 mm. So R we can provide 3 times D, that is 3 times 126, it is 378, or 300 mm. So out of 3, whichever is minimum, that much spacing we can allow maximum, that is provide 8 mm bars at 155 mm center to center. So he has given it is 300 mm. Statement 4 is also incorrect. Which of the above statements are correct? He asked. Only statement 3 is correct. Okay. So the answer A for question number 11. Thank you.